So we started out talking about how Maxwell's equations produces electromagnetic waves, and we're going to continue with that discussion, but we're going to talk about a very specific shape of a wave. Now, it's important to understand that when we talk about electromagnetic waves, that typically what produces them is an oscillating dipole. And, dipoles, again, are basically two charges which are close together, a positive and a negative charge. So, I'll try to draw that out. I'm doing the best that I can. And again, the negative charge is on one side and the positive charge is on the other side. So, we generate radio waves by an oscillating dipole antenna, just two wires, which we alternate the polarity on. And we generate microwaves primarily in a cavity. But again, you can somewhat break down this resonant cavity as having different parts alternating between positive and negative. Molecules will vibrate to produce infrared light. They'll also rotate to produce microwaves. These are all polar molecules. And of course, as we look at even higher frequencies, we end up getting into the visible, where basically we have the atoms themselves with the electrons around them. The electrons are oscillating, producing an oscillating dipole. The inner electrons for ultraviolet light and X-rays, and then of course the nucleus when we're talking about gamma rays. So oscillating dipole, generally what we get is we get these curved surfaces. They're not quite spherical waves that go all the way around the oscillating dipole, but as this thing oscillates up and down, we get these curved waves. And again, we can imagine that this is oscillating up and down, or it's switching its polarity, or it's rotating, or it's vibrating. In any case, it's going to create these curved wave fronts, these electromagnetic waves with a curve, and the curve flattens out. If we go far enough, as we go to the limit where the distance approaches infinity, then we get a flat wave. And this is what we call a plane wave. We have to think about our different analogies here. When we're talking about dropping a pebble into a pond, seeing circular wave fronts, as they propagate out further and further, the circles become large enough, the radius becomes large enough in these circles that they flatten out almost to a line. I mean, this is sort of the same thing, but in 3 dimensions, we're flattening a curved surface into a plane. And again, if we looked at the wavefront itself, we're looking at all one phase. This would be a plane which would be propagating through space with an electric field going in one direction and the magnetic field, of course, perpendicular to that. Okay, so what we're going to do here is we're going to look at the wave equation again, or we're going to create a wave equation, and we're going to see how that results in a solution, which is a plane wave. Now, warning here, I'm going to jump around a lot because really I need to go into vector calculus to a level that really isn't required in this course. And I'm going to need to go into differential equations, again, not required for this course. So there'll be a little bit of hand waving, but I do want you to get a sense of where these different equations come from. And of course, what we generally have, in physics is we have a wave equation, which generally is a description of how the wave behaves, okay? This, if you haven't taken differential equations yet, it is a differential equation. It's actually a partial differential equation. And many systems are modeled such that the rules are contained in the differential equations with different derivatives, okay? Differential equations have solutions, okay? Solutions. And in this case, one of the solutions of the wave equation is a plane wave, a wavefront that forms a plane. You can also have cylindrical waves. You can also have spherical waves. These satisfy the wave equation, okay? But we're going to concentrate on the plane wave. And it's important to understand that we have wave equations in one dimension for a wave on a string. We have wave equations in 2 dimensions for, say, the surface of the water. But the electromagnetic wave is a 3-dimensional equation, and that makes it rather hard to deal with. But again, excuse a little bit of my hand waving. We'll show where everything comes from. And certainly if you want to dive into this deeper, I'm more than happy to go into it. So let's get started. Wow, this looks like a mess, doesn't it? Now, let us remind you of different Maxwell's equations, which are shown here, because this page looks like a mess. But hopefully I can clear it up just a little bit. So here's one of the Maxwell equations up here, okay? This is what we call the curl of E, okay? It basically says that if I have an oscillating magnetic field, all right, that a electric field is going to wrap around this, okay? Oscillating magnetic field produces an electric field, and we might know this in its other form as Faraday's law of induction. We can induce an electric field, okay? And of course, in an induction, we're producing a current, so we're inducing a voltage really from the electric field. So Faraday's law of induction, that's the curl of E. That's where this equation comes from. Okay, what else can we see here? We also see down here, although I put a little slash through it, this is Ampere-Maxwell's law, okay? So we're throwing Ampere out. Ampere came up with this part of it. Basically says when I have a current flowing through a wire, it is going to get a magnetic field curling around it, wrapping around it. So this is the curl of B. So what we see here is our equation for the curl of E, the equation for the curl of B. We're going to put those two together. All right, so let's start with the curl of E. Now, the first thing I'm going to do to the curl of E, and I said there's going to be some hand waving here, so don't get too frustrated with me. I'm going to take the cross products. I'm going to try to take the cross products if I can get the right tool. I'm going to take the cross product of del with respect to this equation. So I'm going to also have a del cross over here. I haven't ignored the negative sign. That's still there. It's just underneath my del cross. I'm going to del cross both sides. Del is our operator with dx, dy, dt, and the unit vectors, okay? And when I do that, I can actually use an identity that we have in vector calculus, and I can replace del cross del with something called the Laplacian. It's basically, instead of dx, I hat, dy, j hat, dz, k hat, it's dd, d squared, it's taking the partial derivative twice, okay? So that is going to go in there on this side of the equation, and it's going to replace it. So now you see that that has been replaced on the left-hand side by that, okay? So that's the first change that I make there. The del cross E is now this one right here. Now I'm going to make the other substitution. I'm going to take the curl of B. I know those of you who have taken Calc 3 are just shaking their heads at this point, but you know, it's good to see this before you actually take an electricity and magnetism course. And I'm going to put this, okay, I'm going to put this in for this, okay? So you notice that this one right here is now replaced by this, which we see over here, okay? So my equation becomes this is equal to this. I'm taking the derivative with respect to time twice of E, epsilon 0 and mu 0 are both constants, so they can go outside this. This now becomes this form, and this right here is a differential equation. It is the wave equation that describes the electric field, okay, in 3 dimensions. All right. What I can do is, because the electric field only oscillates in one direction, is I can align my field such that as the wave propagates, it propagates in the x direction. So I'm going to say, I've got a plane wave here. Oops, not the tool I wanted. I've got a plane wave here. I've got this plane traveling through space. It's going in the x direction. It's propagating in the x direction. So it's just moving along. Just moving along. It's moving from left to right. So this del squared is d dx, d squared dx, I hat plus d dy squared j hat plus d dz squared k hat. Okay? Now, if it's traveling the x direction, there's no change in y. There's no change in z. I can just replace this with this, and now I have a one-dimensional equation, okay? It's one-dimensional, meaning that it only varies in x. My plane's just going to move. It's going to be constant in y and z, but it's going to propagate in the x direction, okay? Now, it's important to understand that the field is still in the y direction for the electric field, or in the z direction for the magnetic field. But the wave, we're interested in how the wave is going to propagate. The wave is going in this direction right there. Okay? So I've tormented you with vector calculus a little bit, but I wanted to show you where this was coming from, that Maxwell's equations do become a wave equation. So here, this is more important than what I just went over. Here is the equation that says, this is how the electric field is going to propagate. Again, if we just allow the wave to go in the x direction only, this is how the wave is going to propagate. These are the rules for the wave. Okay? Now, so this would be called our differential equation, technically our partial differential equation. Basically, these are the rules, okay? How do we play by the rules? We come up with a solution. And the solution, which is really the important part of this section, is this equation right here, okay? Now, this you should be familiar with, okay? From physics 1, did we go over? No, physics 2, we went over waves. But what this equation is just showing us right here, this equation is just showing us right here. Here's our, our different directions. Is we have this electric field, which is oscillating. Okay, it's oscillating, or it's varying in terms of space. So it varies with respect to the x direction, but it also varies with respect to time. So sometime later, we'll get a wave that's moved. Let's say this wave's moved in the x direction. We've got a wave that just moved through its position. So it's oscillating in space and time. Okay, this is very characteristic for second order differential equations, meaning power of 2. Second order differential equations tend to have solutions of sines and cosines. And because this differential equation is second order with respect to space and second order with respect to time, okay, it is oscillating in space and time. All right, maybe you're not convinced. Really, the most general solution for this is to actually have, I've tried to keep it simpler here, but actually add an extra term, which we call a phase, which just shifts this sine or cosine, right or left. All right, so once again, here is a description of the plane wave, okay? We have, this is our x direction, so we're moving through space this way, okay? Moving through space this way, and we have kx, okay? K is what's sometimes referred to as the wave number. It's how quickly it oscillates with respect to space. And then this one you definitely had from Physics 1, omega. Omega is what's known as the angular frequency. It's actually 2 pi times the linear frequency. It's how quickly it's oscillating in time. So K is like a spatial frequency, how many peaks and valleys we have for a given distance, times 2 pi. And then omega represents the angular frequency. Okay, now notice in the other directions, we have this y direction, we have the z direction. This picture is complicated enough that I'm not going to show the magnetic field, but you can clearly see that the electric field sometimes points up in the y direction, sometimes points down in the y direction. And if we were to show this as a vector field, the electric field over all of space, we'd see sometimes it points up, sometimes it points down. That's our plane wave. See, this is one of these planes moving forward in the x direction through space. Okay, so this vector right here is actually pointing in the y direction. Okay, that is the vector that represents more or less the amplitude of the electric field, where, what is its maximum value. But then we multiply by the sine function, which gets it to, oscillate up and down, okay? Point in the positive y direction, then point in the negative y direction. So if I were sitting at a point like this, okay, at this x position right here, I would, let's say it's sort of like, I don't know if you've ever gone to the ocean, watched, birds sitting out on the ocean surface beyond where the waves break, and see them go up and down. You would see the electric field as it passed through you go up and down, up and down, up and down with respect to time. And if you were moving with the wave, you'd have to move at the speed of light. You could ride a peak or you could ride a valley here. And again, here is how we could express. I got the directions a little bit wrong here. But here's how you could express the electric field and the magnetic field for a wave propagating. Remember, there's electric and magnetic fields to this. Here's my expression for the electric field. It's oscillating in the x direction. It's oscillating in the with respect to position and time, but the electric field points in this case should be JK. This shows the Z direction. Okay, we'll have in this case, the electric field oscillating in the Z direction. And in this case, the magnetic field is oscillating in the Y direction. All right, but that's the plane wave. Okay, now again, some important points about the plane wave. Well, we'll go into this in a little more detail. Is that when you're looking at the properties of a wave, okay, K represents the spatial period. Oops, I should probably put it in a different place. K represents the spatial period. So it's equal to 2 pi, okay, over the distance that it repeats itself, what we call the wavelength. All right. So for instance, here's my wavelength lambda. Okay. The higher K is, like if I doubled K, I would have a wave that oscillates even faster. Okay. We'd have 2 peaks instead of 1 between that distance right there. So with K, as K becomes larger, as K increases, the wavelength gets smaller and smaller. All right. So K is like how many peaks and valleys you have for a given distance. Omega represents 2 pi times the frequency, or 2 pi over the period. So in that case there, if I was sitting at some point, the higher omega is, okay, the shorter the period, and the more oscillations would take place at my point. All right. So again, plane wave. If we think about a plane traveling in this x direction, okay, the plane is all distances. It's divided by all of the same distances of x, okay? So for instance, if I were to say x equals 2 is my plane, that looks like x equals z, sorry. X equals 2 is my plane. At a position of 2, everything in the x and y direction would exist in that plane. Okay? I don't know if that's helpful. So let's go on to the next. Here's another important point. One thing that we saw in the equation, if we go back, there was the permittivity of free space and the permeability of free space. These are 2 constants that we use in electricity and magnetism. But going back to this equation right here, this is the equation for an electric field in an electromagnetic wave. But the general equation for any one-dimensional wave, what we'll call U, the wave function, is we can typically write it as this form right here, 1 over v squared, d squared u over dt squared. So this v represents the velocity of the wave. So if I were to equate 1 over v squared equal to mu 0 epsilon 0, what we find is that the speed of the wave is 1 over the square root of these 2 constants, or the product of these 2 constants. Okay? So this equation can be used to describe a wave on a string, can be used to describe plane wave propagating through air for sound. It's the general equation for all waves. But when it's specific to an electromagnetic wave, V is equal to the 1 over the square root of mu 0 epsilon 0. And we know this to be in a vacuum. We know this to be the speed of light. So interestingly, the speed of light is not only equal to this expression right here containing these 2 constants. All right. The other interesting thing we get by going back to Maxwell's equations, we can show this. I won't torment you with it. We can show that C is also the relative strength of the electric field divided by the magnetic field. Okay? Shows that the electric field component is much stronger than the magnetic component. All right? Is that important for our understanding? I think it's important later on when you get into more advanced concepts in optics. And when we think about how light interacts with matter. So for instance, C is equal to 3 times 10 to the 8 meters per second. It's a big number, 2.99, it's a big number. So what it tells us is the electric field has a much stronger impact on the electron in an atom than the magnetic field. Okay, so that when light interacts with matter, it's the electric field that's shaking up the electrons. Okay, the magnetic field doesn't have as much of an impact there. I guess that's one interpretation that you can make there. Oh, I thought I was going to get a nice oscillating picture, but here's our oscillating dipole once again. Just again to understand what is going on here, that really when we generate electromagnetic waves, we're typically doing it with this oscillating dipole, okay? And the wave fronts represent regions where we're all in the same phase, same electric field, same magnetic field. So for instance, if I were to map out what is a constant phase or wavefront, my wavefronts are all curved here. They're all curved, okay? But as it propagates further and further from the time that it's generated, okay, they flatten out, like you can notice here, this field is much more curved than this. Oops, I'm exaggerating. This field right here is flattening out with time. And as we get further and further from our source, it can be an antenna, it can be an atom, a molecule, a nucleus. As we get further and further away, the wave fronts are more plane-like, and they go more to this form that we see right here. Okay. Again, there's a lot going on here, and in terms of understanding, if you come away with anything, I hope you understand how K affects the way the wave looks. K is 2 pi over the period of the wave, and how omega makes the wave look. All right, 2 pi. I'm sorry, I did that backwards. When I'm talking, I don't always. I only have a limited number of brain cells. 2 pi over lambda. Omega is 2 pi over the period. Okay. The bigger K is, the smaller the wavelength. The bigger omega is, the higher the frequency, the shorter the period. Okay. These are the important things to understand, because these go into the solution of the wave equation. So they're going to tell you how a wave behaves. Solutions to wave equations are basically governed by the wave equations. And here's how it oscillates spatially. Here's how it oscillates in time. And this thing right here just shifts it left or right, okay? That always threw me off, this little phi, this little phase thing. But remember, the difference between sine and cosine is just a phase difference of pi over 2. Okay. And let's stop it there.